Welcome back. Let's practice finding limits of functions of two variables. All right, so here's our first example. We want to find the limit if it exists, and if the limit does not exist, explain why. And our given limit here is the limit as xy approaches 3, 1 of the function 2x² plus y. All right, so for any limit that you want to find, the first thing that you should try doing is plugging in the values that you are approaching. In this case, we're looking at the limit as xy approaches 3, 1, or as x approaches 3 and y approaches 1. So what we can do is try plugging in 3 for x in this function and 1 for y in this function. And if we get a real result, then the limit exists. It will be equal to the value that we get. So if we do that here, this will be equal to 2 times 3 squared plus 1, right? We replaced x with 3, so we have 2 times 3 squared, and then we're adding y, which we're replacing with 1. And so simplifying, 3 squared is 9, so this is equal to 2 times 9 plus 1, which is equal to 18 plus 1, which is equal to 19. And so 19 would be the value for that limit. And what that means is that all paths along the surface represented by this function that contain this point lead to a z value of 19 as you approach this point 3, 1 in the xy plane. Okay? Let's take a look at another example. Next up, we want to find the limit if it exists, and if it does not exist, explain why. And this time our limit is the limit as xy approaches 2, 0 of the function 3xy minus 6y divided by x minus 2. All right, so once again, the first thing that you should always try to do is plug in the values that you are approaching. In this case, x is approaching 2, y is approaching 0, so plug 2 in for each x in this function and plug 0 in for each y. If we do that here, we'll get 3 times 2 times 0 minus 6 times 0 divided by 2 minus 2. Right, we replaced each of those x's with 2 and both of those y's with 0. But then simplifying, 3 times 2 is 6, times 0 is 0, minus 6 times 0, which is also 0. So we get 0 in the numerator divided by 2 minus 2, which is also 0. And so we get 0 divided by 0 for this limit, which is an indeterminate form. We cannot determine if the limit exists or not based on that value. So we have to do something else. And the next thing that you could try to do is manipulate your function algebraically such that something will cancel out so that you can then plug in the values that you are approaching. And so can we do that in this case? Well, let's take a look. In the denominator, we just have x minus 2. That can't be simplified at all. But in the numerator, there is a common factor between these two terms that we could pull out. 3xy and negative 6y have a common factor of 3y. So if you pull that out, you could rewrite the limit like this. You'd have the limit as xy approaches 2, 0 of 3y multiplied by x minus 2, right? If you pull 3y out of this term, you'll just be left with x, and then pulling 3y out of negative 6y just leaves you with negative 2, because negative 2 times 3y would be negative 6y. All right, so you have 3y times x minus 2 divided by x minus 2. Now you can see that there's a common factor of x minus 2 in the numerator and denominator that can be canceled out, just leaving you with the limit as xy approaches 2, 0 of 3y. That's it. So now you can plug in the values that you're approaching, 2 for x and 0 for y, or really in this case, all you have to do is plug in 0 for y. There are no more x's in this expression. So this is as simple as just plugging in 0 for y, and you get 3 times 0, which is 0, and that is the value for this limit. The limit does exist, it's equal to 0, which means that all possible paths along the surface represented by this function that contain this point lead to a z value of 0 as you approach this point of 2, 0 in the xy plane. Okay, let's look at another example. For this example, we once again want to find the limit if it exists, and if it does not exist, explain why. And our limit is the limit as xy approaches 0, 0 of the function x minus y divided by the square root of x minus the square root of y. All right, so the first thing that we should do here, just as we've done with the previous examples, is try plugging in the values of x and y that we are approaching. In this case, x is approaching 0 and y is approaching 0. So plug 0 in for x and y in this expression and see what you get. In this case, we will get 0 minus 0 divided by the square root of 0 minus the square root of 0, which will just be 0 divided by 0. All right, that is an indeterminate form. We cannot determine if the limit exists or does not exist just based on plugging in 0, 0 into the function as it is. And so what do we do next? Well, we should try to see if we can algebraically manipulate this function into a form that we could then plug 0 and 0 in for x and y and not get an indeterminate form. And can we do that in this case? Well, initially it might seem like no, because x minus y can't really be simplified, and neither can the square root of x minus the square root of y. But the difference of these radicals should look pretty familiar to something you've done in the past. In particular, I'm referring to one of the methods we used in Calculus 1 for solving limits, particularly limits that involved radical expressions like we have right here. What you can do is try multiplying by a form of 1 using the conjugate of that denominator, or in other words, rationalize the expression, right? What we can do here is multiply by the square root of x plus the square root of y divided by itself. All right, we're just multiplying by a form of 1 because anything divided by itself is 1, and multiplying something by 1 doesn't change its value. Anything times 1 is itself. Okay, and what we're doing here by multiplying by this particular form of 1 using the conjugate of this denominator is we will hopefully get this function in a form that we can actually evaluate at 0, 0. And so let's see what happens when we actually go through with this multiplication. Rewriting the limit, we'll get the limit as xy approaches 0, 0 of x minus y quantity multiplied by the square root of x plus the square root of y divided by the square root of x minus the square root of y times the square root of x plus the square root of y. Now what we want to do is actually multiply these two factors together, and if you're familiar with multiplying an expression by its conjugate, what you'll get is the first term squared minus the second term squared. So you would get x minus y, but just to show you where that comes from, we would have the limit as xy approaches 0, 0 of that same numerator, so just rewrite it again, and then you're dividing by these two quantities multiplied by each other. So you'll take the square root of x, multiply it by the square root of x, that will just be x, then you'll have the square root of x times the square root of y, so you have plus the square root of x times the square root of y, and then you'll have the negative square root of y times the square root of x, so you get minus the square root of x times the square root of y. Those two terms would cancel out. It's just the same term, but one is positive and one is negative, and then take the negative square root of y times the positive square root of y, and you get minus y. All right, so just as I said, all you're left with in a denominator here is x minus y. So I'm just going to rewrite that here. That is what you get when you multiply a binomial quantity by its conjugate. It's just the square of the first term minus the square of the second. So we get x minus y, and that is helpful because now we have a common factor of x minus y in the numerator and denominator that can be canceled out. So you're just left with the limit as xy approaches 0, 0 of the square root of x plus the square root of y. And now you can plug in 0 for x and 0 for y, no problem. You will find that this limit is equal to the square root of 0 plus the square root of 0, which is 0. The value of this limit is 0. Okay, so we were able to show that this limit does exist, even though we seemingly had a complicated function here. We were able to rewrite it in a form where we could plug in the values that we were approaching and get a real value. The limit is 0, meaning that all paths along the surface represented by this function that contain the origin 0, 0 lead to a z value of 0 as they approach that point 0, 0. All right, so that's it for this example. Let's look at another one. Here we once again want to find the limit if it exists, and if the limit does not exist, explain why. And our limit this time is the limit as xy approaches 0, 0 of x plus y divided by x squared plus y. All right, so just like with our other examples, the first thing we want to do here is plug in the values that x and y are approaching. In this case, both x and y are approaching 0, so let's plug 0 in for x and y in this function. So if we do that, here's what we'll get. We'll have 0 plus 0 divided by 0 squared plus 0, which will just give you 0 divided by 0, which is an indeterminate form. We cannot determine if this limit exists or does not exist using this method. But can we manipulate this expression in any way so that we can plug in? Well, not really, right? There's nothing here that we can factor that will then cancel out, and there's nothing to rationalize here because we don't have any radicals, so that's not going to be helpful either. We really don't have a way to simplify this function so that we can plug in 0 and 0 for x and y. So what do we do here? It almost seems like we're stuck. Well, if you watched the lesson video for this topic, then you'll know that when this happens, when you can't plug in the values that you're approaching for x and y, then instead of trying to focus on proving that the limit does exist, we shift gears into trying to prove that it does not exist. And I showed you a method for doing that, which I'm going to review really quickly right here because this is the method we're going to use now. In order to show that a limit of a function of two variables does not exist, what you need to do is show that two paths along the surface represented by that function get different values of z as they approach the point that the limit is approaching. All right, and so to do that, you start by trying the limits for x equals x sub 0 and y equals y sub 0 paths. X sub 0 being the x coordinate that you're approaching for the limit, and y sub 0 being the y coordinate that you are approaching for the limit. All right, essentially what we're doing here is taking turns letting x be a constant and y be a constant, particularly the values from the point you're approaching. And by doing that, you will be rewriting the limit as a limit of a single variable function, which you could then evaluate in each case. And your hope is by looking at the limits for those two paths that they give you different values, right? You want to show that two paths get different values as they approach that point, meaning that along one path on the surface, you're leading to a particular z value, but along another path along the surface, you're leading to a different value of z. When that happens, that means that the limit cannot exist at that point on the surface, okay? Because in order for the limit to exist at a point, all of the paths have to be leading to the same z value along the surface. If you can show that just two paths get different values of z, then that's all it takes to show that the limit does not exist. Okay, so if you can do that for the x equals x sub 0 and y equals y sub 0 paths, then you're done. But if those two limits give you the same value, if both paths from step 1 are equal, then you need to choose another path. And that path will be a function of y in terms of x, or a function of x in terms of y. Right? Y equals f of x or x equals f of y. You just have to make sure that whatever path you choose includes the point that you're approaching for the limit as a point, right? So if the point is 0, 0, like it is in our example, you would want to make sure that whatever path you choose would include that point. Now on top of that, you also want to try to choose a path such that substituting for x or y using that path makes the limit simpler. And you'll see what I mean by that when we get to an example where we have to do this. All right, I'll explain it a little bit further there, but this is the general idea. All right, so this is the process that we use. I know it seems a little bit wordy, it might seem complicated at first, but if we go back to our example here, I think you'll find that the process is not as complicated as it seems. All right, so what we want to do here is we want to try to find two paths that lead to different z values, and we're going to start by looking at the paths where x equals 0 and y equals 0. We're going to take turns setting each of those independent variables equal to the value that they are approaching, resulting in a single variable limit in terms of the other variable that we can then evaluate pretty quickly. All right, so we're going to start by looking along the path x equals 0. All right, so if we're setting x equal to 0, then it is 0. We're going to replace each of these x's in the function with 0, so it's just going to be in terms of y. We're going to have the limit as y approaches 0 of that function. That's it. We don't include x anymore in this limit because we're saying that x is 0 for this particular path. All right, but then replacing x in this function with 0, we get 0 plus y divided by 0 squared plus y. And so simplifying, we get the limit as y approaches 0 of y divided by y. Right? 0 plus y is y, 0 squared plus y is also y. So we have y divided by y in the limit. Well, that's just equal to 1. So we get the limit as y approaches 0 of 1, and the limit of a constant is just equal to that constant. So this limit is equal to 1. All right, so what that tells us is along the path x equals 0 on the surface represented by this function, as you approach the point 0, 0, that leads to a z value of 1. All right, so that's one path that we know where it's heading as it approaches this point, but let's look at another path. Let's look at the path along y equals 0. So let's set that up along y equals 0, we're going to have a limit in terms of x. All right, we're going to do the same thing we did here, but rewrite this function where y is 0. And so you're just going to be looking at the limit as x approaches 0. And that function will be x plus 0 divided by x squared plus 0. I just replaced all the y's with 0 since we're setting y equal to 0, and then simplifying, this limit will be the limit as x approaches 0 of x divided by x squared. That x will cancel out with one of those x's, so we get the limit as x approaches 0 of 1 divided by x. All right, and so what is the limit as x approaches 0 of 1 divided by x? Well, if you think about the graph of that function, that's the reciprocal function. The graph of it looks something like this. So as you approach 0, which would be the y-axis, from each direction you're heading in a different way. From the left side, you're approaching negative infinity, and from the right side, you're approaching positive infinity. So this is a limit that actually doesn't exist. All right, so the limit for the path along y equals 0 does not exist, which you might think is a problem, but that's actually okay. Because what that tells us is that as you approach the point 0, 0 on the surface along the path y equals 0, the limit does not exist, which is different from the limit that we found for this other path. So the limits are not the same, meaning that these two paths do not lead to the same z value on this function, which means that this limit itself must also not exist, okay? In order for the limit to exist, all paths have to lead to the same value. So if we find two paths that do not lead to the same value, even if one of them does not exist, then we know that not all paths go to the same value. All right, so the final answer is this. Since the x equals 0 and y equals 0 paths do not lead to the same value, the limit does not exist. And that's it. That's my final answer to this problem. We did the work showing that the limit does not exist and then explained why. Okay, let's take a look at another example. Next up, we want to find the limit if it exists, and if it does not exist, explain why. This time we have the limit as xy approaches 0, 0 of the function x squared minus y squared divided by 5x squared plus y squared. Okay, so let's begin by just plugging in the values of x and y that we are approaching here. Both of them are 0 once again. So plugging 0 in for x and y, we get 0 squared minus 0 squared divided by 5 times 0 squared plus 0 squared. In the numerator, you're just going to get 0. And in the denominator, you will also get 0 because 5 times 0 squared is 0, plus 0 squared is 0. So we get an indeterminate form once again, meaning we have to find another way to determine if this limit exists or does not exist. If we want to show it exists, there has to be some way to manipulate this function such that we can actually plug in 0 and 0 for x and y. But looking at this function, I don't think there's anything that we can do, right? We could factor the numerator here. This is a difference of squares, x squared minus y squared. You could factor that to be x plus y times x minus y, but that's not going to do anything for us because it doesn't cancel out with anything in the denominator. So we're kind of stuck with this function as it is. We can't manipulate it in any way, so plugging in is not going to work. Instead of trying to show that this limit does exist, let's shift gears and try to show that it does not exist, because that's most likely going to be the case here. And so to do that, we want to show that two paths along this surface, as they approach this point, lead to different values of z. So we start by looking at the paths x equals 0 and y equals 0. The paths where we set x and y equal to the values that they are approaching. So let's begin by looking along the path x equals 0. Let's set x equal to 0 for this limit. We're just going to have a limit in terms of y, so y will be approaching 0, and then replace all of the x's with 0. So we have 0 squared minus y squared divided by 5 times 0 squared plus y squared. And then simplifying, we'll have the limit as y approaches 0 of negative y squared divided by y squared, right? 0 minus y squared is just negative y squared, and then 5 times 0 squared is 0, plus y squared will just be y squared. Now those y squareds will cancel out, and so this will be equal to the limit as y approaches 0 of negative 1. And that's just a constant, so the limit will be equal to that constant. We get negative 1 as a result of this limit. So along the path x equals 0 on this surface, as we approach the point 0, 0, the path is leading to the z value of negative 1. All right, and so let's compare that to what we find if we travel along a different path. Let's look at the path y equals 0. All right, so along y equals 0, our limit will now be in terms of x. X will be approaching 0, but now rewrite the function here, replacing each y with 0. So we have x squared minus 0 squared divided by 5x squared plus 0 squared. That will be equal to the limit as x approaches 0 of x squared divided by 5x squared, right? 0 squared is 0, x squared minus 0 is x squared, and then 0 squared plus 5x squared is just 5x squared. Now those x squareds will cancel out, just leaving you with the limit as x approaches 0 of 1/5. And that's just another limit of a constant, so the result will just be that constant of 1/5. And so, that is good. That's exactly what we were hoping to find here. As you travel along the path y equals 0 on this surface, and you approach the point 0, 0, the path is leading to a z value of 1/5. That is different than what the x equals 0 path led to. It led to negative 1. So we have now shown that along this surface there are two paths that as they approach this point 0, 0, they are leading to different values of z. So the limit cannot exist. So our final answer here would be since negative 1 does not equal 1/5, the limit does not exist. That would be my final answer to this problem. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful, then I'd like to invite you to join my membership site, JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. So if you are interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's take a look at the next example. For our next example, we once again want to find the limit if it exists, and if the limit does not exist, explain why. And our limit is the limit as xy approaches 0, 0 of the function 3xy squared divided by 4x squared plus y to the power of 4. Okay, so just like with our other examples, let's begin by first trying to plug in 0 and 0 for x and y. We want to plug in the values that they are approaching into the function. And so let's see what we get. We'll have 3 times 0 squared divided by 4 times 0 squared plus 0 to the power of 4. In the numerator, you're just going to get 0, and then in the denominator, 4 times 0 is 0, plus 0 is 0, so we get 0 divided by 0. That is an indeterminate form. And looking at our function here, there's nothing we can do to simplify it. There's no way to rewrite this function such that something cancels out and we can plug in 0 and 0 for x and y. So there's really no way for us to show that the limit does exist here. Instead, we want to try to show that this limit does not exist. That's our new plan here. And so just like with the last two examples, let's try showing that there are two paths along this surface that contain this point that lead to different values of z. And we're going to start by looking at the paths of x equals 0 and y equals 0. You always look at the paths where you set x and y equal to the values that they are approaching. So we're going to look first along the path x equals 0. And so let's rewrite the limit, but where x is 0. So we're going to have the limit as y approaches 0, right? Y is still approaching 0, and our limit will be in terms of y. But then replacing these x's with 0, we will get 3 times 0 times y squared divided by 4 times 0 squared plus y to the power of 4. If we simplify that, 3 times 0 is 0 times y squared is 0. So the numerator is 0. We get the limit as y approaches 0 of 0 divided by 0, right? 4 times 0 squared is 0, plus y to the power of 4. So we have y to the power of 4 in the denominator, but really that doesn't matter. 0 divided by that value is just going to be 0. So we get the limit as y approaches 0 of 0, which will just be equal to 0. All right, so that's what we get for the limit along the path x equals 0. But now let's look at the path y equals 0. Along that path, we're going to rewrite this limit, but set y equal to 0. So we're going to be looking at the limit as x approaches 0 of 3x times 0 squared divided by 4x squared plus 0 to the power of 4. And so simplifying, the numerator will just be 0 because anything times 0 is 0. So we get the limit as x approaches 0 of 0 divided by 4x squared plus 0. So we get 4x squared in the denominator. But just like our limit up here, 0 divided by that value will be 0. So we get the limit as x approaches 0 of 0, which is equal to 0. And that is not what we're looking for. All right, we have just found that there are two paths, x equals 0 and y equals 0, along this surface that as they approach the point 0, 0, lead to the same value of z. Now that doesn't prove that the limit exists because we would have to show that all paths lead to 0, but it also doesn't prove that the limit does not exist, right? We have to show that there are two paths that lead to different values of z. We have not done that yet, so we have to pick a different path. This is the first example in this video where we've gotten to this point, but I did talk about what we need to do here when I reviewed our process for showing that a limit does not exist earlier in this video. Remember how we talked about that if these two paths, if their limits give you the same value, you have to pick another path to work with, particularly a path that contains the point that your limit is approaching. And on top of that, you also want to pick a path such that when you plug in for x or y in the limit, it becomes a nice limit to solve. In other words, there should be some nice simplification that can be done. All right, so we're either going to pick a path that is y equal to a function in terms of x, or x equals a function in terms of y. It all depends on what's going to make this function easier to work with. And the way I like to determine this is by looking at the denominator. Specifically, what could I do to either x or y such that when I make a substitution, I could combine those terms in the denominator. Usually if you can figure that out, the numerator will also simplify nicely based on that substitution. All right, and so looking at what we have here, x is squared and y is to the power of 4. If we let x equal y squared, then y squared squared would be y to the 4th power. We would then be able to add these two terms together because they both would be y to the 4th power. That seems like a good idea. And it will be because in the numerator, if this x is replaced with y squared, you'll have y squared times y squared, which will be y to the 4th power. So you'll have y to the power of 4 in both the numerator and denominator, which will make for some nice cancellation and ultimately a nice limit to evaluate. That's what we're looking for here. That's going to help us find a limit that gives us a different value than 0. All right, so let's look at that path. Let's look along the path x equals y squared. And this path does contain the point 0, 0, right? If you plug 0 in for x and 0 in for y, you'll get 0 equals 0, which is a true statement. So that's good. You want to make sure that the path that you choose does contain the point that you're approaching. So we're good there. If that was not the case, we would want to pick a different path, but we don't have to worry about that here. Let's rewrite this limit using that substitution of x equals y squared. All right, so we're going to be rewriting the limit in terms of y. So we will just be working with a limit in terms of y. We'll be looking at the limit as y approaches 0. All right, we're replacing x with y squared, but y is still approaching 0 for that limit. All right, so we'll have 3 times x, which is now y squared. So y squared times y squared divided by 4 times x squared. So you'll have y squared squared plus y to the power of 4. And so simplifying, we get the limit as y approaches 0 of 3y to the power of 4 divided by 4y to the power of 4 plus y to the power of 4. All right, y squared times y squared is y to the 4th power, and so is y squared squared. You get y to the 4th power times 4. Then combining these two terms, 4y to the power of 4 plus y to the power of 4 will be 5 times y to the power of 4. So this is equal to the limit as y approaches 0 of 3y to the 4th power divided by 5y to the 4th power. And then those y's to the fourth power cancel out. So you're just left with the limit as y approaches 0 of 3/5, which will just be equal to 3/5. And that's what we are looking for. We have now shown that along the path x equals y squared on this surface, that as you approach that point 0, 0, the path leads to a z-value of 3/5. And that is different than what we found for these two paths. Really, you only need to compare it to one of them. As soon as you find two paths that don't lead to the same value, then you have successfully shown that the limit does not exist. All right, so our final answer here is that since 0 does not equal 3/5, we're just comparing the z-values that we found for the limits along different paths. Since those are not the same, the limit does not exist. All right, that is the final answer to this problem. Next up, we once again want to find the limit if it exists, and if the limit does not exist, explain why. And our limit this time is the limit as xy approaches 0, 3 of the function 4xy minus 12x divided by x² plus y² minus 6y plus 9. All right, so just like with all our other examples, what we want to do is first just try plugging in the values of x and y that we are approaching. So in this case, we'll plug 0 in for x and 3 in for y. So if we do that here, we'll have 4 times 0 times 3 minus 12 times 0 divided by 0 squared plus 3 squared minus 6 times 3 plus 9. Now, in the numerator, 4 times 0 times 3, that's 0, minus 12 times 0, that's also 0. So we just get 0 in the numerator, and then in the denominator, 0 squared is 0, plus 3 squared, that's 9, minus 6 times 3, that's 18. So we have 9 minus 18, which would be negative 9, and then you're adding 9 to it, which takes you back to 0. So this is in an indeterminate form of 0 divided by 0, so we cannot determine if this limit exists or does not exist in its current form. Perhaps there's a way that we can manipulate this function such that something cancels out so we can plug in the values that we're approaching. And so you do want to consider that, but I don't know if it's going to be possible here. But let's take a look anyway. In the numerator, there is a common factor of 4x in both of these two terms. You could divide out 4x from this term and this term. So let's do that. Let's pull it out. This will be equal to the limit as xy approaches 0, 3 of 4x times y minus 3. Right? If you pull out 4x from this term, you're just left with y, and pulling 4x out of negative 12x leaves you with negative 3. So we have 4x times y minus 3 in the numerator, but is there anything that we can do in the denominator? Well, nothing is going to cancel out. We're not going to be able to find a factor of 4x or y minus 3 in every single part of this denominator, although I do see a quadratic expression here that we could factor. We have y squared minus 6y plus 9. Since the coefficient of the squared term is 1, you could easily factor this by looking at the constant term and asking yourself what two factors of that number added together give you the coefficient of the middle term. And in this case, negative 3 times negative 3 is positive 9, and negative 3 plus negative 3 is negative 6. So that would factor to be y minus 3 times y minus 3. So you could rewrite that quadratic in this way, which would also be y minus 3 squared. All right, so we could do that here. We can definitely factor, but it's not going to do much for us right now. Rewriting that denominator, we have x squared plus y minus 3 squared. But we can't cancel anything out here. You can't cross out this y minus 3 and cross out one of these, because when you cancel out a factor, it has to be a factor of every single part of the fraction. It's not a part of this x squared term, right? This x squared would also need to be multiplied by y minus 3 in order to cancel that factor out within this function. So there's nothing we can do here to make this function any simpler. Okay, so it doesn't really seem like we're going to be able to plug in the values of x and y into this function in order to show that the limit exists. So at this point, I think we need to pivot and instead try to show that this limit does not exist. And I'm going to keep this work here. It might become helpful later on as we try to show that the limit does not exist. It might be easier to refer to the limit in this form. So don't erase this work. It may not have been for nothing. But let's actually try to show that the limit does not exist here by finding two paths that lead to different values of z. And we'll start by looking at the paths where we set x and y equal to the values that they are approaching. So we're going to look along two different paths. We're going to look along x equals 0, right? X is approaching 0. So we're going to look at that path, x equals 0, and we're going to look at the other path, which would be y equals 3 in this case, right? Y is not approaching 0 this time, it's approaching 3. So don't use the path y equals 0 because that doesn't contain the point 0, 3. You need to use this path y equals 3 instead. All right, but let's look at these two paths and compare the result of the limits. Starting with x equals 0, let's rewrite this limit, but replace each of those x's with 0. And I am going to work with the limit in this form, by the way. I think it will make it easier to work with. But when we set x equal to 0, the limit will be in terms of y. So we're going to be looking at the limit as y approaches 3, right? Y is still approaching 3, even when we set x equal to 0. But then replacing each x with 0, we get 4 times 0 times y minus 3 divided by 0 squared plus y minus 3 squared. All right, now in the numerator, you're just going to get 0 because you have 4 times 0 and then 0 times that quantity. The whole thing just becomes 0, so you have the limit as y approaches 3 of 0 divided by that denominator, which will just be y minus 3 squared because you're just adding 0 to it. So you have y minus 3 squared, but that will just be 0 divided by that quantity, which will be 0. So you'll have the limit as y approaches 3 of 0, which will just be equal to 0. All right, so that's what we get for the limit along x equals 0. As you travel along that path on this surface and approach the point 0, 3, the path leads to a z value of 0. But let's compare that to along the path y equals 3. If we let y equal 3 in this limit, it will be in terms of x. So we're going to be looking at the limit as x approaches 0 because x is still approaching 0, even when y equals 3. And then we want to replace each of these y's with 3. So you'll have 4x times 3 minus 3 divided by x squared plus 3 minus 3 squared. All right, now 3 minus 3 is 0, so you have 0 times 4x in the numerator, which is just 0. So you get the limit as x approaches 0 of 0 divided by x squared, right? 3 minus 3 is 0, 0 squared is 0, 0 plus x squared is x squared. So you have 0 divided by x squared, which just like this limit over here, 0 divided by that value will just be 0. So you'll have the limit as x approaches 0 of 0, which will just be equal to 0. All right, and that's not what we were hoping for, right? We were hoping that these two paths would lead to different values of z. But we have just shown that both of these paths, x equals 0 and y equals 3, along this surface, as they approach this point, lead to the same value of z, z equals 0. So we have to find another path here. All right, we need to choose another path that will not lead to 0. And to help us find that, what we need to do is choose a path that first of all contains the point that we are approaching for the limit, but also leads to a nice substitution for x or y in this limit. And this is where our simplification from earlier will now become helpful, because in its original state, this limit is not entirely clear what kind of substitution we can make, because our goal is to make the limit as simple as possible. The way I usually like to think about it is what can I set x or y equal to such that a substitution would allow me to combine all of the terms in the denominator. And looking at these terms here, x squared and y squared minus 6y, that's going to be hard to get all of them to combine, let alone the fact that you have that constant of 9 on the end there. All right, and choosing a path also isn't going to be easy because it has to include that point 0, 3. So you couldn't just test substituting y in for x or x in for y because the line y equals x would not include this point of 0, 3. Same thing with y equals x squared or x equals y squared. Those two curves or those two paths do not include this point, so you couldn't even try those substitutions here if you wanted to. So in this form, this limit is very difficult to see what type of substitution we can make or what type of path we could choose that would help us show that the limit does not exist. But rewriting it in this form helps us see that a little bit better, because there is that common expression of y minus 3 in the numerator and denominator. It may not be in every single part of the expression, such that we can cancel it out, but it does repeat itself, so maybe we could use that to our advantage and pick a path where we set x equal to y minus 3. That's actually going to be pretty nice, because if y minus 3 is x, then you'll have x squared plus x squared. You can combine those two terms and have one term in the denominator, which is typically what we're aiming for. Similarly, in the numerator, if y minus 3 is x, you'll have x times 4x, which will be 4x squared, which is also just one term, specifically a term with the same variable part as the denominator. Both of them will be x squared terms. That would be perfect. That's exactly what we want here. So that's going to be our other path. I'm going to choose to use the path along x equals y minus 3. And that path does contain the point that our limit is approaching. If you're not sure, plug in 0 for x and 3 for y, and you'll get 0 is equal to 3 minus 3, which results in 0 equals 0, and that's a true statement. All right, so this is a good path to choose here. So let's set up our limit. If we're replacing y minus 3 with x, then our limit will be in terms of x. So we're going to keep it as the limit as x approaches 0, because x is approaching 0, but then replace y minus 3 in both places with x. So we'll have 4x times x divided by x squared plus x squared, which simplifies to the limit as x approaches 0 of 4x squared divided by 2x squared. And then we can cancel out those x squareds because anything divided by itself is 1. So you'll just have the limit as x approaches 0 of 4 divided by 2, which would be 2, right? This would be the limit as x approaches 0 of 2, which equals 2. And that is what we were hoping for. That is a value that is different than what we found for our other paths. We have just shown that along this path, x equals y minus 3 on this surface, that as you approach this point 0, 3, the path leads to a z value of 2. That is different than 0, which means that we have now shown that there are two paths on the surface that contain this point that lead to different values of z, which means that the limit cannot exist. All right, so our final answer here is that since 0 does not equal 2, I'm just comparing the two different values of z that we found that our paths lead to. Since those are not the same, the limit does not exist. That is the final answer to this problem. Okay, so we found the limit does not exist, and we have the work to back that up. We are done with this limit. All right, let's take a look at a different type of example. Here we want to find the limit using polar coordinates. And this is something that you can do. Sometimes you will be given a limit of a multivariable function, specifically in this case one of two independent variables, that would be easier to evaluate if you just rewrote it in terms of polar coordinates, because if you do that, it will become a limit of a single variable, which we are familiar with evaluating. All right, our limit here is the limit as xy approaches 0, 0 of cosine of x squared plus y squared. Sure, you could evaluate this limit in terms of x and y. You could plug 0 in for x and 0 in for y and have cosine of 0, which is 1. But another way that you could do this is to use polar coordinates. Remember that to convert from rectangular to polar coordinates, that r squared is equal to x squared plus y squared. You can make use of that fact right here. You can replace x squared plus y squared with r squared, and then you'll have a limit as r approaches some value, which will be 0 from the right. And the reason for that is because if x and y are approaching 0, then in this equation, you would have r squared equals 0. Solving for r gives you r equals 0 as well. But x squared plus y squared will never give you a negative value, so r would only ever be positive. So rewriting this limit, you would have the limit as r approaches 0 from the right of cosine of r squared. All right, you replace x squared plus y squared with r squared, and now you have a limit in terms of polar coordinates that is equivalent to this limit of a multivariable function. So then all you have to do is plug 0 into the function, and you'll find that this is equal to cosine of 0 squared, which is cosine of 0, which is equal to 1. That is the value of this limit using polar coordinates. All right, so be on the lookout for limits of multivariable functions where that expression x squared plus y squared shows up, because if you see that, you could convert that limit into polar coordinates. And so let's take a look at another example of this. Here we once again want to find the limit using polar coordinates, but this is a more complicated limit this time around. We have the limit as xy approaches 0, 0 of x times y squared divided by x squared plus y squared. If you were to try to evaluate this in terms of x and y, you would get an indeterminate form, right? If you plug in 0 for x and 0 for y, 0 times 0 is 0, divided by 0 plus 0. So that would be 0 divided by 0. which means that you would either have to manipulate this into some form so that you could plug in 0 and 0, which I don't think you can do here. So instead, what you could do is rewrite the limit in terms of polar coordinates. Now, this is a little bit more involved this time because we don't just have x² plus y squared, we also have an x and a y squared in the numerator that we have to convert, but that's no problem because we can use some other formulas for converting from rectangular to polar to help us out, right? So not only do we know that r squared equals x² plus y squared, but we also know that x is equal to r times cosine theta and y is equal to r times sine theta. So let's use that here. Once again, we will rewrite the limit to be the limit as r approaches 0 from the right, but then rewriting the rest of the limit in terms of polar coordinates, we get this. x² plus y squared will become r squared. And then we need to replace x with r cosine theta and y with r sine theta. So we'll have r times cosine theta, but then y is being squared, so you'd get r squared times sine squared theta. All right, and now you can see that we have an r squared here and an r squared here that would cancel out. So cross those out, and you'll just have the limit as r approaches 0 from the right of r times cosine theta sine squared theta. Now, this might look tricky at first, but remember that this is a limit in terms of r. We're looking at what happens to r as it approaches 0 from the right. We don't really care about cosine theta or sine squared theta. If you just plug 0 in for r, you will get 0 times cosine theta sine squared theta, which will just be 0. So you get a limit of 0, and that would be the value of this limit. All paths that contain this point along this surface as they approach this point lead to a z-value of 0. Okay, let's take a look at one more example for this video. For our last example, we once again want to find the limit using polar coordinates, and we have the limit as xy approaches 0, 0 of sine of the square root of x² plus y squared divided by the square root of x² plus y squared. All right, now once again, you could plug in 0 if you'd like for x and y, and you would find that you would get sine of 0, which is 0, divided by the square root of 0, which is also 0. So you would have an indeterminate form of 0 divided by 0. So using polar coordinates here could be helpful. It could hopefully help us avoid that indeterminate form. So let's see what happens here. We only need to make use of one formula here. We have x² plus y squared in both cases. So we just need to remember that r squared equals x² plus y squared. So rewriting this limit, we'll have the limit as r approaches 0 from the right. All right, once again, that does not change. That's always going to be the case. If x and y are approaching 0, then r will approach 0 from the right. But then we're going to have sine of the square root of r squared divided by the square root of r squared. Now, the square root of r squared will be r, so we can simplify both of those. This will be equal to the limit as r approaches 0 from the right of sine r divided by r. Now, if we plug in 0 here, we will get 0 divided by 0, right? We would have sine of 0 divided by 0, which would be 0 divided by 0. Sine of 0 is 0. So that's an indeterminate form, which is not great. However, unlike our original limit, this is a limit of a single variable function. So we can use L'Hopital's rule. We can take the derivative of the numerator and denominator since our limit is in the form of 0 divided by 0. So let's do that up here. Rewriting our limit again, we'll have the limit as r approaches 0 from the right, and we're going to use L'Hopital's rule. And so taking the derivative of the top, the derivative of sine r will be cosine r, and then the derivative of r is 1. So you have cosine r divided by 1. Now if you plug in 0, watch what happens. You get cosine of 0 divided by 1, but I'm not going to write that. And then cosine of 0 is equal to 1. That is the result of this limit. We have now shown that all paths along this surface that contain this point, as they approach that point, they lead to a z-value of 1. Okay? And so that's it for this example, and this was also the last example for this video. But if you want to get some more practice finding limits of functions of two variables, I do have some more examples available on my membership site. So if that's something that interests you, feel free to look into becoming a member. You can find all the details on my website at jkmathematics.com/plus. If you have any questions, please let me know in the comments. But if you don't have any questions, this is all I had for now, so I will see you next time.